Hi class, today we're going to be working on something completely different than what we've been looking at before. We're going to be talking about sets. Well, what are sets? So by the end of this lesson you'll know what a set is. You'll know how to write a set in two different forms. You'll be able to find and identify subsets within a given set. You'll understand the universal set and what a complement of a set is. So what is a set? A set is just a group of numbers. More specifically, the definition says it's a collection of distinct elements. Some examples of sets are real numbers, rational numbers, integers, odd numbers, multiples of 3, or any collection of numbers at all. So I can just create an arbitrary set, and sets are always defined by braces. And I want my set to include 1, 5, A, 8, and 15. That's a set. It can be any collection of numbers. I have a reason for picking these numbers potentially, but just know that a set can be anything. Sometimes it's specific, sometimes it's not so specific. There are two ways to write a set. There's the roster form, which is, as I just showed you, is just a list of the elements within braces. So if you were to write odd numbers, you could write a brace 1, 2, 3, 5, 7, 9, etc. Multiples of 3 would be 3, 6, 9, or any random group. The other way to write a set is called set builder notation. And you may see this a lot of times with what we've just been working with is inequalities. Sometimes it will require you to write an answer in set builder notation. And we'll get into that later in the chapter. But for right now, all you need to know is that set builder notation describes the property an element must have to be included in the set. So for my random group, there might not be a property involved to be a part of that set. So in that case, we would not be able to write it in set builder notation. However, a lot of times you'll have something like this. And what this means is we have, this reads as x such that, is a line up and down, x is a multiple of 3, or is an odd number. So it puts properties to all of those elements. So x such that x, which means you have a variable x, and that x must be an odd number. All right, or x has to be a multiple of 3, which is what this example says. All right, so you would read that as x such that x is an odd number. When we start using inequalities, we would write x such that x is greater than or equal to 3. That's a set builder notation for an inequality. So again, here are some examples. So the question might say, how do you write T is the set of natural numbers that are less than 6 in roster form and in set builder notation? So if you had to write it in roster form, natural numbers, so remember natural numbers are counting numbers, so 1, 2, 3, 4, so on, that are less than 6. So if you're going to put it in the roster form, which is you're listing all the numbers, then you have to list 1, 2, 3, 4, and 5. However, set builder notation allows us to write it in a way that it includes everything with a restriction. So here it says x, which is the variable, such that that x is a natural number, but, which is the comma, x has to be less than 6. All right, and again, this stuff may seem silly or unnecessary, but it has a use when we start working with more complex numbers and bigger numbers or bigger sets of numbers, where you don't want to list out 50 numbers. You just want to be able to identify it by a set. So here's how we would use it when solving an inequality. So in set builder notation, how do you write the solutions of negative 5x plus 7 is less than or equal to 17? You would solve it the same way. You would subtract 7 from each side. You'd have negative 5x is less than or equal to 10. Divide by negative 5, so you flip the sign. The 5 should cancel. And you end up with x is greater than or equal to 2. So if you were to write that in set builder notation as I showed you on the last slide, we would write the variable, which is x, a line, and then what the inequality is. So x is greater than or equal to negative 2. So this B would be our answer. Now subsets of a set. So a set A might be a subset of a set B if each element of A is also an element of B. So in order for something to be a subset, it must be included in the regular set. So here's my example, set B, and this is how you would write maybe set B if you were to label something set B, equals 1, 2, 3, 4, 5. Then A would be a subset because it has 1, 3, 4. So A is a set by itself, but A is also a subset of B. So another example might be if you have the set of odd numbers, a subset of that may be 1, 3, and 5 by itself. So the way we would write this is this tells us that A is a subset of B, and we would write that in math language as A is a subset of B, or A is contained within B, is another way of saying that. Now there's also something called the empty set, which is simply a set that does not contain any elements at all. And this is written like this. It's a 0 with a line through it. That's how we're going to write the empty set. So sometimes you may want to use the empty set to show that there is no answer within the set, or the empty set is actually included in all sets. So it is possible that something isn't a part of the set. That's why the empty set is always a subset of every set. So here are some example problems of what you may see for now dealing with sets. So you may be asked, what are the subsets of the set 1, 2, 3, 4? So maybe we should call this set C equals 1, 2, 3, 4. So the empty set is always a subset, as I mentioned before. So we're going to write the empty set. So you also have 1 is a set, 2 is a set by itself, 3 is a set. So all sets with only one element are subsets. And I apologize for the chicken scratch. Okay, and then you would go to possibly the 2-element subsets, which are listed below. And then the 3-element subsets, and finally, the whole set itself is a subset of itself. So there's two quirky things with subsets. One, the empty set is always a subset of any set, and the set itself is also a subset of the original set. So this is going to help us develop a pattern that we'll look at later called Pascal's triangle, but that gives us a total of 16 subsets. Finally, we have the complement of a set. So in order to understand complement, we must understand the universal set, which is labeled as just a capital U, which is the largest set you are using, or the set that represents everything. So you see below, the universal set may be all real numbers, right, which includes lots of things, and a subset of all real numbers, or a different set within the universal set, may be irrational numbers. Okay, so if we're using U as the universal set of all real numbers, if A is the set of rational numbers, then we would say the complement of set A, which is rational numbers, would be irrational numbers. It would be everything in the universal set that is not in the set A. So the complement of a set is a set of all elements in the universal set that are not in the set. So if the universal set was odd numbers, or let's do it this way. If the universal set was natural numbers, so remember, natural numbers are counting numbers, 1, 2, 3, 4, 5, etc. And then you had a set A, which was odd numbers, then your complement, which we would write as A with a little comma, that comma is called prime. So we would say this is A prime, or some people refer to that as not. So this would be not A. So if A is odd numbers, not A is even numbers. It's everything that is not included in the set but is contained within the universal set. And again, I know some of this may seem a little confusing. That's okay. You will understand, these are things that you'll understand more as we do some examples of. So here's an example of a complement. I think I just used this one, so I was jumping ahead of myself, but here it is written down a little more cleanly. So if you are given that the universal set U is natural numbers and the set A is odd numbers, then the question might ask you, what is the complement of A, or A prime, or not A? Not A would then just be even numbers. And again, if you look back, you will see that that could be written as which means not A contained in the universal set, or not A is a subset of the universal set. So what we learned today, we learned about universal sets, empty sets, roster form, set builder notation, subsets, and complements. We will go through this in live class again, and I think as you see the problems, you will start to understand that this just puts some uniformity into things, and you'll gain a better understanding of what this is. Good luck with the lesson, and I will see you guys in live class.